Okay, this is the first video on section 2.3, compositions of linear transformations and matrices. So the big idea sort of here is that linear transformations are well behaved with each other. So they compose well. We saw in 2.2 that linear transformations u plus t could come together and that you could scale linear transformations, but we'll see things like compositions of linear transformations in here, or the composition of a linear transformation and the sum of linear transformations. And ultimately what we'll see is really three operations. You can add linear transformations, you can multiply linear transformation, which is composition, and you can scale them. And together, for those of you that are familiar with the term, that will show us that linear transformations from V to V form an algebra. Now, that's not something that will be defined in this term. It would be in an abstract algebra course, but it's addition, multiplication, and scaling all interacting well. So let's move on to the theorems. The first theorem says if you have three vector spaces, V, W, and Z all over the same field, with T going and T a linear transformation from V to W, and U a transformation from W to T, then the composition UT from V to Z is also linear. And the proof is pretty straightforward. Remember, one way to show linearity is to show addition in one step and scaling in another step. Another way to do it is just to do them both in the same step. So if you pick two things in the domain, and you pick a scalar, we want to see what ut of cx plus y is, right? Well, what is ut defined to be? Well, it's defined to be u of the output of t of this. And then, as in most linear algebra proofs, we get linearity by borrowing linearity. Well, t was linear. That was our assumption. So what's that mean? That means t of cx plus y is c tx plus ty, right? And since these are elements of w, right, we get linearity from u also. So we get c of utx, if we're being technical, u of t of x plus u of t of y. And of course, what does this mean? Well, this means that when we think about ut as a single function, we get exactly linearity, right? This is a laundry list of things. Let's imagine that t is a linear transformation and u1 and u2 are linear transformations from V to V. Well, you could add two linear transformations and then compose. That's the same as composing and then adding the outputs. You could compose on the right. You could compose and then compose in either order. It's associative. These are the things that really go back to, you can sort of see, yes, this is sort of the definition of algebra. You could take the identity transformation, that does nothing, and then t, or do t in the identity transformation, that's t. Most of these are just following I should say all of these are just following the definition. You can scale at any point in this operation and it behaves well. Let's just do the proof of B together to give you a flavor of these. So how are you going to show two functions are equal? Well, two functions are equal if they have the same domain, and for anything in the domain, right, they have the same output. So let's see, what is u1 plus u2 composed with t of x? And I'll dispense with writing the extra parentheses, right? The definition of this is t of x is an output, right? So what's the definition of that? That's u1 of t of x plus u2 of t of x, right? Well, what is that? That's just the definition of u1t of x plus u2t of x, which is really the definition of addition of two functions. And of course, what I've done here is I've shown that these two functions have the same output for every input. So that's the end of part B. Okay, so this is probably the most, tedious of the theorems here somehow. Notice if you have linear transformations, t going from v to w and u going from w to t, then you can take the coordinate matrices corresponding to ordered bases, alpha, an ordered basis of v, v, beta, an ordered basis of w, and gamma, an ordered basis of z. And you can multiply those coordinate matrices, and that's the same as the coordinate matrix corresponding to ut in terms of alpha and gamma. So this, I'm just going to give you the proof idea. So first off, you need to recall what matrix multiplication is. Think about it precisely. Well, what is the ijth entry of the matrix AB? Well, you might remember from back in the day, how do you multiply two matrices? You go row, column, right? This is the ith row times the jth column, which when we're writing this precisely, you sort of go through the index 1, 1, 2, 2. So k from 1 to n of a, I, k. This is the entry I1, I2, I3 up to IN, times b, k, j. This is the entry 1j, 2j, 3j. And so that's the definition. So that's really what matrix multiplication is, but let's think about what's actually happening over here, okay? So what is this matrix here? T from alpha to beta, right, corresponds to taking, let's see, t of alpha to beta, right? That corresponds to taking the jth, if you think about this matrix, what does the jth column look like over there? The jth column over there, let's think about that as like b1j down to bnj. Those are the coefficients of t of alpha j in terms of the basis beta. So we got beta 1, b1j out to bnj for bn, right? That's really what this column is, right? Well then, what would the ith row of u beta gamma be? Well, if you think about that, if that was like a I1 out to a I n, and incidentally, to multiply these matrices, that n has to be the same, right? What is that? Well, that's, say, taking for each beta k, right, this is taking a specific input and getting all of the coefficients. This is saying, well, for a beta k, what is the coefficient that goes in front of the gamma I term, right? So that row has all of the coefficients for the gamma I, right? So I guess I'd write A I K there, right? That particular term there. So what happens if you multiply these matrices together? Well, so think about that. What you've got over here is you want to know what is the output of ut on alpha j, right? But I really only want to know, let's say I'm looking at ut alpha gamma, and I'm just looking at the ij coordinate. What is the ij coordinate of this matrix on the left? Well, it's saying if you take ut of alpha j, what is going to be the coefficient on the gamma ith term, right? On the gamma ith term. Well, t of aj is going to be this thing in here, right? It's going to be the sum of the b k j's for k equaled 1 to n, and then u of each of those terms, u of each of these terms, is going to take that beta, put it in here, and get out a I k, right? It's really the matrix multiplication. It's this row times that row. That is going to be exactly the ij coefficient, and that's exactly matrix multiplication. So that's why this theorem is true.